Hello and welcome to this lecture where we will start discussing beams. Let's look at what happens in the hollow vaulting pole during its bending. We'll consider a part of the pole before and after bending. The pole bends into a circular arc, and as a result, the side of the pole on the external side of the arc will elongate while the opposite side will shorten. The elongated part is in tension, while the shortened part is in compression. As we can see, one of the sides of the pole will elongate, the top side in the picture on the right, and the opposite side will shorten, which is the bottom side in the picture. Inside the pole, the elongation will gradually decrease, turning into shortening. The change in the elongation and shortening within the beam cross-section is assumed linear, which can be seen in the picture on the right. The axis of the pole will not undergo any deformation, since it represents the boundary between elongation and shortening. As a result, one half of the pole will be in tension, shown in red in the picture, while the other part of the pole will be in compression. The maximum tension and compression will develop on opposite sides of the pole. Beams are one of the main structural elements. They carry loads primarily by bending through developing tension and compression on opposite sides. A beam subjected to gravity load sags. The top of such a beam will be in compression and shorten, while the bottom will be in tension and will elongate. In addition to bending, beams carry shear across the depth of the cross-section. There is a direct similarity in the behaviour of trusses and beams. In general, trusses can be seen as beams with holes. Beams can have solid cross-sections. Such beams are usually made of timber or concrete. Beams can also have more complex shapes of cross-sections like I, H, T, C, O, box, and many more. Such beams are usually made of metal such as steel and aluminium, but can also be fabricated from timber or concrete. As we discussed, a beam curves in a circular arc. This leads to shortening of one part of the beam due to compression, and elongation of the opposite part of the beam due to tension. At the level of the centre of gravity, or the centroid of the cross-section, the beam does not deform. This level of the beam is called the neutral axis. The deformation of the beam changes linearly from elongation to shortening. This results in the maximum elongation and shortening developing on the opposite sides of the beam, while the neutral axis does not change in length. In the beam considered on this slide, the maximum elongation develops on the top side, while the maximum shortening develops on the bottom side. Since deformation is directly connected to loading, the most deformed parts of the beam will be the most loaded. In the beam considered on this slide, the maximum tension will develop on the top side of the beam, and the maximum compression will develop on the bottom side of the beam. The middle part of the beam is relatively not loaded. Since the top and the bottom of the beam are the most loaded, it is structurally prudent to put more material in those areas. The middle of the beam is less loaded and requires less material. These principles are reflected in the shape of an I-shaped cross-section, which is extensively used in structural engineering. To understand how beams work, let's consider a beam with a span L loaded by a concentrated load P as shown. The reaction forces in the beam can be found using the three equilibrium equations. The right reaction is 0.4p, while the left reaction is 0.6p. We'll now use the imaginary cut technique to look at what happens inside the beam. Let's create an imaginary cut at half the distance between the left support and the concentrated load P. We'll now examine the forces required at the imaginary cut in the beam, which are needed to preserve equilibrium. To preserve the equilibrium of forces in the horizontal direction, an internal force should be added at the cut. This internal force is called the axial force and is always in the direction of the beam. To preserve the equilibrium of forces in the vertical direction, an internal force should always be added to the cut. The internal force is called the shear force and always acts perpendicularly to the direction of the beam, which means to its axis. And to preserve the equilibrium of moments, an internal bending moment should be added at the cut. After cutting the beam, we separate the parts. Since the original beam was in equilibrium, each part of this beam will also be in equilibrium. As you can see, both parts of the beam are not in equilibrium in the current state. This can be easily seen on the right part of the beam. The translation equilibrium of the horizontal direction can be achieved through the addition of the axial force N at the cut. As you can see, the force N is added in opposite directions at the cut in both parts of the beam. This arrangement will cancel the force N if the beam is connected back. The translation equilibrium in the vertical direction can be achieved through the addition of shear S at the cut. As you can see, the force S is added in the opposite directions at the cut in both parts of the beam. This arrangement will cancel the force S if the beam is connected back. And the rotational equilibrium can be achieved through the addition of a bending moment M. The bending moment is also added at both parts of the beam in opposite directions. The internal forces can be found from equilibrium equations written for only one part of the beam. As a result, it's convenient to select a part which has easier geometry and a smaller number of forces. But what we need to remember is that these are internal forces and moments, and when we bring the beam back together, they should always cancel each other out. In the cross-section considered, we can see that in the horizontal direction there are no forces, and therefore from equilibrium, the axial force N is 0. In the vertical direction, and for the selected direction of the shear force S, the sum of vertical forces on the left part of the beam gives us a shear force equaling to 0.6 P. And for the selected direction of the bending moment M, the sum of moments in the left part of the beam about the point of the cut gives the internal moment of 0.12 PL. Note the units, force times distance, for the moment. Let's move the cut by 0.1 L towards the concentrated load P and find the axial force, the shear force, and the bending moment. The sum of forces in the horizontal direction in the left part of the beam still equate to 0. In the vertical direction, the shear force still equals 0.6 P. And the sum of moments of the left part of the beam around the point of the cut gives us a bending moment of 0.18 PL. As a result, we can see that both the axial force and the shear force didn't change while the bending moment grew. Let's see what happens when we have a distributed load. The action of the distributed load can be substituted with an equivalent force acting at the centre of gravity of the load. The bending moment at the cut can be found from the sum of moments around the point O located at the cut. And the bending moment equals the sum of the moments generated by the reaction force L and the distributed load. The shear force can be found from the sum of forces in the vertical direction, and the shear force equals the sum of all the distributed load and the reaction force applied at the considered part of the beam, taking into account the directions of forces. The values of axial force, shear force, and bending moment change along a beam. It's convenient to show these changes using diagrams. We'll consider several examples of beams subjected to different loading arrangements and discuss their axial force, shear force, and bending moment diagrams. First, let's consider a simply supported beam loaded by a concentrated load of 50 kN at midspan. The beam has symmetric geometry and load, and therefore each of the vertical reactions will equal half of the load applied, which is 25 kilonewtons. There are no horizontal forces, so the axial force along the beam is 0. The shear force and bending moment diagrams are shown below. Let's discuss features of both diagrams. In this discussion, we will start from the left end of the beam and proceed towards the right end. The shear force diagram will be discussed first. The shear force diagram starts on the left side of the beam where the shear force is 0. At the left support, the reaction force of 25 kilonewtons is directed upwards, and this force lifts the level of the diagram to plus 25 kilonewtons. Since the part of the beam between the left support and the concentrated load at midspan is not loaded by any other external force, the shear force stays constant, and the diagram in this part continues as a horizontal line at the level of plus 25 kilonewtons. The concentrated load of 50 kilonewtons lowers the shear force diagram from the level of plus 25 to the level of minus 25 kilonewtons. The part of the beam between the concentrated load and the right support is not loaded by any external force, and here the shear force stays constant and the diagram continues as a horizontal line at the level of minus 25 kilonewtons. The reaction force of 25 kilonewtons at the right support lifts the diagram from the level of minus 25 to 0. And on the right hand of the beam, the shear force diagram continues at 0. Let's now discuss the bending moment diagram. This diagram also starts on the left from the beam at zero level. At the left support, the reaction force makes the diagram change direction. Since the reaction force acts upwards, the change in direction occurs clockwise. The part of the beam between the left support and the concentrated load at mid-span is not loaded by any external load. Here the diagram continues as an inclined line. At mid-span, the concentrated load makes the diagram change direction again. Since the concentrated load acts downwards, this change in direction occurs counterclockwise. The part of the beam between the concentrated load and the right support is not loaded by any external force, and in this part the diagram continues as an inclined line. The reaction at the right support makes the diagram change direction. Since the reaction force acts upwards, the change in direction occurs clockwise. And on the left of the beam, the bending moment diagram continues at zero. As you can see, the deformed shape of the beam sags, where the compression side of the beam is at the top and the tension side is at the bottom along the entire beam. The bending moment diagram is drawn on the tension side of the beam. As you can see, all the beam is in sagging bending. In addition, the bending moment diagram has three extreme points at the breaks caused by the reaction forces and the concentrated loads. These points occur where the shear force diagram crosses zero. At the left support, the shear force diagram crosses zero by moving upwards, and therefore the bending moment diagram develops a maximum at this point. At mid-span, the shear force diagram crosses zero by moving downwards, and therefore the bending moment diagram develops a minimum at this point. And at the right support, the shear force diagram crosses the zero level by moving upwards, and therefore the bending moment diagram also develops a maximum at this point. Since the structural geometry and loads are symmetric, the shear force diagram is antisymmetric, and the bending moment diagram is symmetric. Another example that we'll consider is a 5-meter long simply supported beam loaded by a uniformly distributed load of 25 kN per meter. The total load acting on the beam is the load times the span, which gives us 125 kilonewtons. Due to symmetry, the supports develop similar reaction forces, which equal 62.5 kilonewtons. There are no horizontal forces in this example, so the axial force is zero across the entire beam. Let's look at the shear force diagram. The shear force diagram starts on the left side of the beam, where the shear force is zero. At the left support, the reaction force is directed upwards. This force lifts the diagram to plus 62.5 kilonewtons. The beam is loaded by the uniformly distributed load of 25 kilonewtons per meter, and this is directed downwards. The shear force diagram becomes an inclined line, decreasing by 25 kilonewtons for each meter. At the right support, the level of the diagram decreases to minus 62.5 kilonewtons. The reaction force of 62.5 kilonewtons at the right support lifts the diagram from the level of minus 62.5 to zero. And on the right of the beam, the shear force diagram continues at zero. Let's now discuss the bending moment diagram. This diagram also starts on the left of the beam at zero. At the left support, the reaction force makes the diagram change direction. Since the reaction force acts upwards, the change in direction occurs clockwise. Under the uniformly distributed load, the bending moment diagram curves. Since the uniformly distributed load acts downwards, the diagram gradually curves counterclockwise. The reaction force at the right support makes the diagram change direction. Since the reaction force acts upwards, the change in direction occurs clockwise. On the right of the beam, the bending moment diagram continues at zero level. As you can see, the deformed shape of the beam sags, where the compression side of the beam is at the top and the tension side is at the bottom along the entire beam. As we said before, the bending moment diagram is drawn on the tension side of the beam. In addition, the bending moment diagram has three extremums, two at the supports and one at mid-span. These extremums occur where the shear force diagram crosses the zero level. At the left support, the shear force diagram crosses the zero level by moving upwards. Therefore, the bending moment diagram develops a maximum at this point. At midspan, the shear force diagram crosses zero level by moving downwards. Therefore, the bending moment diagram develops a minimum at this point. And at the right support, the shear force diagram crosses zero level by moving upwards again. Therefore, the bending moment diagram also develops a maximum at this point. Since the structural geometry and loads are symmetric, the shear force diagram is antisymmetric, and the bending moment diagram is symmetric. Let's now quickly summarize the features of the shear force and bending moment diagrams we've seen. The shear force diagram is horizontal at beam parts without loads. The bending moment diagram is straight and inclined at beam parts without loads. The shear force diagram jumps at point loads. The slope of the bending moment diagram breaks at point loads. These breaks are clockwise where the shear force diagram decreases and counterclockwise where the shear force diagram increases. The shear force diagram slopes under distributed loads. The bending moment diagram curves under distributed loads. And the shear force diagram is zero at both ends. Additionally, the bending moment is zero at free ends. The bending moment diagram develops extremums where the shear force equals zero. If the structural geometry and loading are symmetric, the shear force diagram is antisymmetric, and the bending moment diagram is symmetric. There is a connection between the shear force diagram and the bending moment diagram. The shear force diagram is the differential of the bending moment diagram, and the bending moment diagram is the integral of the shear force diagram. Thank you for joining me for this session. Now that we've covered the introduction to beams, I hope you join me next time where we will discuss in a bit more detail how to approach solving beams.